Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, good. So we're really happy to have two guests from NICT, Hitoshi Isahara and Kiyotaka Uchimoto. And they're going to be the first, Mr. Isahara is talking to us about resource-based NLP, and then Mr. Uchimoto is going to be talking to us about his experience in working on Japanese, Chinese, both directions, empty, and Japanese, English, both directions, empty. So those three languages that they're focusing their 5-year project. The NICT has been collecting lots of resources for NLP, not only Japanese, but in many languages. And so he's going to tell us all about it first. Thanks.
Okay, so today I talk about some resource-related research works at NICT. Now it's very obvious. So recently, huge database of actual text is available as a reliable information source, and there are many researches on natural language processing which is based on such databases. We can call it linguistic resources. And as for the relation between linguistic resource and technologies, we have two viewpoints. One is the NLP technology is useful to compile linguistic resources. That's one thing. And also, NLP technology can utilize such resources and extract useful information. And of course, there's no clear cut between these two kinds of technologies, compilation and utilization. Then, I'm from NICT. NICT stands for National Institute of Information and Communication Technology, and we have several branches. Our headquarters is in Tokyo, and our branch is in the south end of Kyoto Prefecture. We have 4 research groups in Kyoto. So one of them is our research group. It's a computational linguistic group. Here we have 3 research projects. One is our own project, Linguistic Information Project, and other 2 is Language Grid Project, which combine NLP technologies and resources and makes the actual service. And the third one is Thai Computational Linguistics Laboratory, which is located just north of Bangkok. So they are doing the research on Asian, especially South Asian languages. And NICT is National Institute of Information and Communication Technology. It's a kind of national institute. Then we are developing very useful technology. Useful, I mean it's widely applicable and with high performance. And also we are developing huge linguistic resources. And that's because we are a kind of national institute, and our aim is make these things open to the public. And this one, so the technology and resource is one of our research axes, and the other axis is forefront research and very practical development. As for forefront research, for example, we automatically extract the semantic relation among words from huge amount of corpora. So this 3-dimensional semantic map is one of that output. And also we are now doing some practical development project. So it's a research and development of Japanese-Chinese and Chinese-Japanese both direction machine translation system. Here, our translation engine will be based on example-based machine translation, and here syntactic information will be used in many parts of the translation engines. So the analysis and corpus compilation and alignment and so forth. So this is a very rough sketch of our system. So input is scientific and technical papers, like the journal papers. The input is Japanese or Chinese, and we have analysis engine and translation engine. Then our output is also scientific and technical style of papers. So because we utilize an example-based mechanism, we have to make a huge corpora between Japanese and Chinese, and also we need some dictionaries to analyze input text and examples. So this project is funded by Japanese government. We have some mission statements. So our goal for the third year is to evaluate the Japanese-Chinese one direction. Japanese from Japanese to Chinese machine translation prototype system for specific target domains. For example, the information science domain. And the goal for the fifth year is the end of our project. We have to improve the Chinese analyzer and complete the demonstration experiment on the Japanese to Chinese and Chinese to Japanese machine translation prototype system. So this project is not only our institute, NICT, but also we have some teams of 5 institutes. It's NICT and Kyoto University, Tokyo University, Shizuoka University, and JST. JST stands for Japan Science and Technology Agency. So they have a huge amount of text data, especially the journal papers, and also they have a huge amount of abstracts of such journal papers. So one of our targets is make a translation system which can translate such text into Chinese. Okay, so because we are developing, for example, we are developing the machine translation system using example-based mechanism, we have to make a huge amount of linguistic resources. So we already developed several kinds of huge corpus, which includes NICT Multilingual Corpus, it's Chinese-Japanese English corpus, and large-scale Japanese-Chinese parallel corpus. And as for Japanese to English, Japanese and English, we have several corpora, such as newspaper article parallel corpus, novel parallel corpus, patent parallel corpus. And for Japanese corpus, we have Corpus of Spontaneous Japanese. And as for learner's corpus, English learner corpus, we have NICT JLE corpus. JLE stands for Japanese Learner English. So Corpus of Spontaneous Japanese, we developed it under one of the Japanese national project in collaboration with the National Institute for Japanese Language. So National Institute for Japanese Language is very much a linguistic side. And our institute is, we can say, it's a very technology side. So this project is the combination of these two kinds of research institutes. And this is a large scale of spontaneous speech corpus of common Japanese. Common Japanese means it's not a very specific dialect. It's commonly used in Japan, especially for example, in Tokyo. And the name of the project was Spontaneous Speech Corpus and Processing Technology. And the contents is mainly of monologues, about 10 to 15 minutes a lecture. So it's something like the talks that now I'm doing. So we have 2 types of speeches. One is academic presentation speech, and the other is simulated public speech. So we think it's a fruitful resources for research of spontaneous speeches. For example, speech recognition, automatic summarization, linguistic research, and so on. So Japanese National Institute of Japanese Languages records all such speech data and transcribe everything. And then we automatically analyze such text and annotate it morphologically. And also we have several subcorpus, such as sentence selection, syntactic dependency corpus, and discourse structure corpuses. We extract such information from the original huge corpus. And next, I would like to talk about the newspaper alignment data. So now in Japan, several newspaper text is available for research purpose. And one of such corpora is Yomiuri Shimbun Corpus. Yomiuri Shimbun is one of the Japanese biggest newspaper companies. We can use Japanese text of Yomiuri Shimbun from 1987. And that company, Yomiuri Newspaper Company, issues Daily Yomiuri. It's English newspaper. So, but it's not a direct translation. It's different paper. But the content is rather similar. So we can say these two texts are comparable corpus. So both are available for academic and business use. We extract the sentence alignment and article alignment from these text data. And as for the sentence alignment, we extracted 180 sentence pairs. And as for articles, we extracted 95,000 article pairs. So those are now available for business for academic purpose free of charge. And we just started to sell this sentence pairs for business purpose. And we recently create a patent corpus, which contains 2 million sentence pairs. So we'll make it open to the public shortly.
Are the patents actually translated
From Japanese to English? So that patent is firstly applied in Japan. Then the
patent was filed internationally.
Yeah. So those two patents have the same numbers. So we can firstly extract such pairs. Then we use our alignment technology to extract sentence pairs. So this is a kind of information retrieval systems, cross-lingual information retrieval systems. Suppose we Japanese people read the Japanese newspaper, the articles in Japanese newspaper. So it's this article is on the president election in United States. Then someone who is reading this article wants to know more about this article. So they can use this system and extract the similar articles in English. So our system analyzes the content, the title of this article, and extracts the candidate of equivalent using our parallel corpus. Then, using these candidates, we could extract the English newspaper articles. Because we have the Thai branch in Thailand, so we extend this Japanese to English system into Thai to English system also. One of the features of this system is this system automatically extracts the equivalent using the parallel corpus, not a dictionary lookup. So, for example, it's my experience. I was reading the newspaper articles about the political issues in Myanmar. So there's a famous participant is Aung San Suu Kyi. But I don't know how it spells. But this system has a parallel corpus, and it can extract the candidate of the English transliteration of Aung San Suu Kyi. So we could extract the English articles about such Myanmar's political issues.
What is this in the bottom? You have boxes. Can you click them?
Yeah.
Check them and uncheck them if they're not relevant.
Yeah. We can check the most appropriate equivalent. But normally, the first candidate is the best candidate. And also, we are comparing the multilingual annotated corpus. It's Japanese, Chinese, and English. So this project started in 2002, and will open this corpus into public shortly. So the focus of this corpus is Asian language. So now we studied Japanese, Chinese, and English and Japanese. So annotated with detailed information such as syntactic structure and alignment at word and phrase levels. So the source of this corpora is, one source is Japanese newspaper article, around 38 kilo sentences. So we manually translate it into Chinese and Englishes. And another source is English. We extract the sentences from pen Treebank and translate it into Japanese. It's 18 kilo sentences. But we have some, copyright problems. So we quit this part. Now we are comparing this part only. So as for the Japanese-Chinese part of this multilingual corpus, it's high-quality Chinese translations from Japanese newspapers. It's Mainichi newspapers. It's a different company from Yomiuri newspaper companies. So annotated with detailed information. Details, I mean the morphological and syntactic information, and being in accordance with existing tag sets developed by the Chinese universities. And they have the alignments at word level and phrase level. And we also developed a tool for annotations. So our input is 38,383 sentences. It means in Chinese, it's around 900,000 words and around around 1 million characters. As for the lexical resource dictionaries developed at NICT, we have EDR Dictionary, and we start the development of Japanese WordNet and also the Asian, especially Southeast Asian WordNet. And we have some small Kyoto sightseeing dictionary. And as a part of our machine translation project, we are now compiling a huge Chinese-Japanese dictionary. EDR Dictionary, it's a huge electronic dictionary between Japanese and Chinese. So there are several sub-dictionaries. It's a word dictionary, bilingual dictionary, concept dictionary. It's a core of this EDR lexicon. And concurrence dictionary and technical terminology dictionaries. Now we are extending it into Chinese. So we are making the Chinese word dictionary as a part of this EDR dictionary, and we will make it open to the public maybe at the end of this Japanese fiscal year. I mean, it's by April 2008. And we just started our project to develop a Japanese WordNet. So last fiscal year, we add the Japanese word to the synset of Princeton WordNet. So we extract around 10,000 synset. It means around 30,000 words. And this fiscal year, we add more Japanese words, and also we are trying to make the real Japanese WordNet. Real, I mean, it's not the direct translation, but we'll add some new synset to the Princeton WordNet. And also we are thinking to make some linking from WordNet to EDR lexicon. So we already have some corpora which is annotated with EDR concept IDs. So once we have some link between WordNet to EDR, we have some big set of linguistic informations. And our Thai branch is now started to make the Southeast Asian WordNet. So now the language included is Thai, Indonesian, and Mongolian languages. And as a part of this resource compilation, we opened the homepage named LinguaPark. So there people can retrieve some information using our corpus. It's one of the screenshots of our corpus. It's maybe English-Japanese novel corpus. So Alice's Adventures in the Wonderland and Through the Looking Glass, such things. Okay, now I change the object. So this is not a compilation of linguistic resources, but the pure research. So we are thinking to extract some knowledge, useful knowledge from linguistic resources. We think the meaning of words can be defined by their usage only. So, and also the meaning of words varies with text. It means the contents, domain, style, and so forth. So we are trying to extract linguistic information from corpora based on its linguistic phenomena, or we can say based on collocations. So now we are doing the research on automatic extraction of lexical knowledge from corpora. So firstly, we make the collocation information into collocation vectors. So for example, Japanese word kimochi is collocated with these Japanese adjectives, glad, sad, happy, and so forth. Then we'll make the vectors like this. The kimochi, the vector for kimochi is like this, and the omoi is like this, and so forth. Now in our experiment, the total number of the nouns, especially the abstract nouns, is around 300, and the number of different adjectives, which is co-occurred with, which modified those abstract nouns, is around 10,000, and the total number of adjectives is around 35,000. So using this kind of data, we could extract these three-dimensional semantic maps. Here we use complementary similarity measure as a measure of inclusion. So the usage of this word is included by the usage of that word and so forth. So which means hierarchical information. I think this kind of information, semantic map, is very useful for several kinds of NLP applications. So now we are extended our technology to Chinese, this one thing, and also we think this kind of things is useful for extract the domain-specific knowledge. And in future, we can use some semantic analysis using this kind of relations of word meaning. Using this kind of technologies, I mean the extraction of word meaning from huge corpora, one of our research is query suggestion. It's not a simple query expansion. We could suggest people, so this word is maybe very useful for your future retrieval and so forth. Okay, our research question is, what kind of words are useful for directing users to informative pages on the web? Then what kind of relation between the previous keywords and the additional words is effective for retrieving more informative pages? Then we are now trying to extract thematically, non-taxonomically related word set from documents and verify the usefulness of the extracted word set as keyword for word retrieval. So the three-dimensional semantic map I showed is a kind of taxonomical relation, hierarchical relations. But in this research, we'd like to extract relations, thematical relations from corpora. So I think there's at least two kinds of relations between words. It's taxonomically and thematically. Taxonomical relation is kind of hierarchical relations, horse and cow and animal and so forth. Thematic relation is not taxonomically. So for example, it's a relation between milk and cow as collected in milking cow. So this information includes associated, causal, and entailment relations. So how to extract word set with thematic relations? So very roughly speaking, we extract many kinds of relations from corpora and remove the set of words which have the taxonomically relations. So firstly, we extract many kind of relations, and then we remove the taxonomically related word set. Taxonomically related word set, here we mean the word set which agree with the thesaurus. Then the rest of the word set extracted is word set with the thematic relations. So now we are trying to extract such a thematic relation in medical domains. So we are using the Japanese document in the medical domain. It contains around 200,000 sentences. And as for the pre-coded thesaurus, we use the medical subject heading thesaurus, mesh thesaurus. And Japanese medical terms, which are equivalent of descriptors in the mesh thesaurus, we are using as a technical terms of our experiments. So it's around 2,500 terms in the document. So these are the examples of extracted word set. We think it's a kind of thematically related word set. So overlays, flame, palpation, and variation, cross reactions, outbreaks, circulation, and so forth. So we'd like to verify whether it's useful for information retrieval or not. So we use a word set like this. So one word in this word set has a different category, and other words in this word set is the same categories. And creates 3 types of such terms from each of these kind of word sets, and compare the result of word retrieval by using 3 types of word set as input. Okay, the first one is like this. So all word is in the same category. I mean, this is the all word is related taxonomically. And we add one word why it's a different category, and also we add one word which is the same categories. So we have three types of word set. So word set type 2, we think that suppose the type 2 is the original input, the user inputs type 2 keywords. Then as a next step, user add one word which relates non-taxonomically, or the user input one more word which relates taxonomically. Okay, this is a result of quantitative evaluations. So if user adds one word which relates taxonomically, the number of extracted pages is similar to the previous input. But if user adds one word which relates thematically, the number of extracted pages is decreased. So at least quantitatively, the thematically related word is useful to pilot users to informative, or at least the specific informations. It's one thing. So next, we evaluate quantitatively. So this is some interesting examples. So we use word set, latency period, erythrocyte, and hepatic cell. So more informative pages are ranked near the top by adding latency period, it's thematically related words, than hepatic cell, it's a taxonomically related words. So actually the top page retrieved by latency period and erythrocyte is about malaria. So if we use thematically related words, these two words, we could extract many pages which has no relation about malaria. So new knowledge can be obtained from informative pages retrieved by adding a thematic related terms. It's a qualitative evaluations. So in this research, our conclusion is like this. So we try to extract WordSet with a thematic, at least non-taxonomical relation from documents. And we verify the usefulness of such WordSet as keywords for information retrieval. And we found thematically, at least non-taxonomical related terms are effective as additional terms for retrieval support. And the thematic relation seems to be quantitatively and qualitatively more effective than the taxonomical relation for information retrieval that find unknown or interesting ones unexpectedly. So we back to the original topic. So resource and technology. So at NICT we are developing the NLP technology, which is widely applicable. For example, machine translation, resource compilation, and language grids. And also we are developing natural language resources, which will be used for our own project, such as machine translation project, and also make them open to the public. So this is our homepage. Some of our research topics is explained in this homepage. Okay, thank you very much. Actually, our experiment is done in a medical domain. So it's because we have, of course we have EDR Lexicon, but it's a general purpose. So we need some specific domain-specific thesaurus. So far we have is only for such a medical domain. So we checked only that medical domains. So I think even in a medical domain, this kind of thematic relation is very useful. So that's all what I did. So.
Good afternoon. Today I have two topics to talk about, and if I have enough time, I will move on to the next topic. The first topic is construction of large Japanese-Chinese aligned parallel Treebank Corpus. And this is the outline of my talk. And we are compiling Japanese-Chinese parallel Treebank Corpus because a publicly available Japanese-Chinese parallel corpus is rarely found. And this compilation is done in two ways. One is a human translation, and the other is to induce parallel corpora from noisy parallel corpora. And for the second one, we are we are taking the we are employing the method presented at ACL 2003, and today I'm not going into the detail for this second part. And we are also developing analyzers and aligners, and by using these analyzers and aligners, we are going to annotate linguistic information to this corpus. And it's done in semi-automatic way. And the number of parallel sentences we are going to compile is 1 million sentence pairs. And it will be, the compilation will be finished in 3 years. And this is the second year. And now about 80% of these sentences will be finished. The compilation of the 80% will be finished in this fiscal year. And the target domain is scientific area, scientific field. And now we have one of our project member is JST, Japan Science and Technology Agency, and they have a database of scientific papers, and they are providing a service of information extraction of scientific papers. And according to the access to the database, we have selected target fields, main target fields. And they are information science and biological science and environmental science. And we have been and we are now negotiating with academic societies and to give us a permission to use the scientific papers. And now we have over we have received the permissions from over 30 academic societies. And now we have over 30,000 papers, and it will become over 1 million sentence pairs, 1 million sentences. So we have selected 1 million sentences from the scientific papers based on coverage. And and we have selected a dense set of papers, sentence sets, according to the mainly word statistics. And we are going to annotate linguistic information such as morphological, syntactic, and sentence or phrase and word alignment information to the parallel corpus in semi-automatic way. And that will be used as examples for our EBMT system. And they are also used for training analyzers. And this is the example of our annotation. And each sentence is word segmented and POS tagged. And word and phrase information, phrase alignment is assigned to. And dependency information is also assigned to each sentence. And next, I'd like to talk about human translation. And part of the human translation is done based on replacement. And this is the human translation support tool based on replacement. And this tool, by using this tool, the user can this tool show the user several translation candidates according to the translation memories. And this tool can also keep the history, translation history, like this. And in the early stages, mainly words are replaced with target language words. And in the next stage, the longer parts, or longer words or phrase or clauses are replaced with target language phrase or clauses, like this. And we found that we can acquire phrase, quasi-word phrase alignment and quasi-syntactic structures from the translation history. For example, this is the original sentence, and this is the translation, its translation. And we obtained this kind of bracketed, embedded structures from the translation history. And by eliminating these target information, target language information from here, we can obtain this bracket information and alignment information. And this bracket information indicates a certain structures like this. And it sometimes corresponds to the linguistic structure, but sometimes not. But we believe that we can, this kind of information helps us annotate the parallel corpus efficiently. Next, I'd like to talk about analyzers and aligners. As for alignment, we have developed several techniques, and now we are integrating the techniques. And today I'd like to talk about these analyzers. As for Japanese analysis, JUMAN is used for morphological analysis, and KNP is used for dependency structure analysis. And these systems are publicly available systems. And given a sentence, first it's word segmented and POS tagged. And then bunsetsu or boundaries are found. And then the dependencies are detected like this. And these are automatically, yes. And the case structure analysis is also done, and it's used for improving the dependency structure accuracy and the alignment performance. Case structure analysis, for example, for this sentence, for the predicate, this one is verb, and this verb has several case markers, ga and kara, and for each case markers, now this one and this one can be with these case markers. Yeah. Surface case relationship is extracted as case in this case structure analysis. And they are used to detect the omitted information, and they are used to alignment, used for alignment. Case information, if there is the omitted information such as a subject, it's detected by using the case structure. And if we have the contextual information, we can detect what kind of information is missing. And that information can be used to align between two sentences. And yeah. Okay, okay. And the detail was presented at NASL in 2006. And as for Chinese analysis, it's done in the same way. First, word segmented and POS tagged. And after chunking, the dependency structure is detected. And we compared several approaches for this analysis. As for Chinese word segmentation and POS tagging, we compared three approaches: word-based, character-based, and hybrid approaches. And we found that the hybrid approach achieved the best accuracy. And this, the detail was presented at ACL in 2006. And in this hybrid approach, known words are mainly detected based on a word-based approach, and unknown words are detected mainly based on character-based approach. And given sentence, in general, a lattice structure is constructed, and each node corresponds to a word in word-based approach, and each node corresponds to a character in character-based approach. And in hybrid approach, each node corresponds to a word or a character. So given a sentence, the part of speech information is assigned to a node that is found in a dictionary, for example, like this. And otherwise, the chunking labels is assigned to. And the chunking label is defined within a start-end scheme. And then the path that maximizes the probability, the product of probabilities is extracted as an optimal path. Next, as for Chinese chunking, the problem was solved as a sequence labeling problem. So, given a sequence of words, for each word, chunking label is assigned to. And then, according to the chunking label, the chunk boundaries are detected, like this. And we have developed two chunkers. And we also combined two chunkers by using a voting method. And we also used a low corpus to improve the accuracy. And we found that over 91% if measure was achieved by using this method. And this work was presented at ACL 2006. And as for Chinese dependency structure analysis, we employed the shift-reduce parsing algorithm. In this algorithm, for example, given a sequence of words with part of speech information, in the first step, the first two words is examined, and if there is the relationship between the two words, if there is no relationship between the two words, these words are shifted to the stack, and for the next words, the relationship is if there is a relationship between the next two words, like this, the child node is reduced, and then the next two words, the rightmost word in the stack and the leftmost word of the remaining input words are examined, and if there is a relationship or there is no relationship, in the same way, the relationship is detected like this. And by this algorithm, by using this algorithm, we found that 85.2% of dependency accuracy can be achieved when we use the Pen Chinese Treebank Corpus. And for this is the baseline, and for further improvement, we think it's important to detect and use reliable information. In the conventional methods such as self-training, automatically analyzed sentences all of them are added to the training data. So the unreliable results are included in the training corpus. That is a problem. And this figure shows the relationship between the dependency length and the F measure. And the dependency length is defined as the distance between two words that have dependencies. And as you can see, a good accuracies can be achieved when the length is short. So we use this part of information that we call the dependencies whose dependency length is short. It's short dependencies, and we utilize this information. We used people daily corpus, and they were automatically analyzed. And we used two words having short dependencies for training. And we found that the dependency accuracy is improved by 1% from the baseline method. For example, by using the initial model or baseline model, for this example, it was not correctly analyzed. It was analyzed like this. This means expert level working discussion. And we found that the first one and third word are found in a low corpus with short dependency, like this. So we, by using the short dependency, by extracting the short dependencies and use them as features, we found that this example can be correctly analyzed like this. And this work will be presented at IJC NLP next year. And we are developing two types of parsers, one for dependency structure analysis and one for phrase structure analysis. As for phrase structure analysis, we used statistical lexicalized model that was firstly proposed by Collins. And in this structure, in this analysis, this kind of output can be obtained. And we found that a phrase structure model achieved higher accuracy than the dependency structure model. I think this is because more information such as NP and VP phrase labels are used in the phrase structure analysis, and more information helps to improve the accuracy. So, maybe the global information can be utilized by phrase structure analysis. And this work was presented at PACRIN in 2007. And then I'd like to introduce the semi-automatic analysis. The method is followed. We followed the framework presented at IGCAI 2007. And this is the overview of the framework, annotation framework. In an usual setting, we have small annotated corpus with high accuracy and a large raw corpus. And usually, corpus-based system is used because it's robust to the change of annotation tag sets. And in the initial step, we think we need to detect errors in the annotated corpus. The errors can be detected by comparing the annotated corpus with the results obtained by using corpus-based system trained by using annotated corpus. And in the analysis of the raw corpus, it's important to detect unreliable parts, and it's also important to amend the dictionary and the features by correcting the errors, unreliable parts in the raw corpus. And also, enhancement of the linguistic resources is important, and it's done by using active sampling. By using this framework, we'd like to reduce the human labor costs. So we are developing several annotation tools. This is the tool for annotating morphological information. And by using this tool, unknown words can be detected, and error candidates can be easily examined. And user can access to the dictionary information, and also user can access to words in the annotated corpus, already annotated corpus. And we are also developing several other annotation tools, such as for syntactic and alignment information. This is a summary of the first topic. I have introduced the work for constructing a large Japanese-Chinese aligned parallel Treebank corpus, and we introduced a method for how to use translation history. And I described our analyzers and aligners, and the semi-automatic analysis method. And we are now improving the performance of Chinese analysis and word or phrase alignment performance, and now constructing annotated corpus. That's all for the first topic. If we have
so first of all, I just wanted to get a reference from you. You had some work on extracting syntactic structure based on the replacement-based translation.
Yes.
It sounds interesting. I'd like to just have you done a paper.
It's not yet published.
Oh, it's not
Yeah,
published?
yeah.
Oh, okay.
This one. Okay. Yeah.
But it's not yet published?
Yeah. Not yet. I'm now. And I have to submit the paper. So. Dependency structure, not only and alignment, yeah.
And also I was wondering, your co-training results are very encouraging. Your self-training results, sorry. Have you, but I wonder, so your training, the additional training data only comes from short dependency links, right?
Yeah.
So I wonder what happens to your accuracy. Like this is, go back one slide. This is your original accuracy before
Yes.
co-training, before self-training, right?
Yeah.
Have you done a similar graph after self-training? Does accuracy improve across the board, or are you only improving accuracy on the short links that were there?
We have tested it by with self-training, and it also the accuracy was improved. But we found that the short dependencies the accuracies with shorter dependencies outperform the performance of self-training.
So by doing self-training for short sentences, it went worse?
Pick up better overall, but worse on the short links? Is that?
Short links information. Short link information was used as feature sets, and we used all of the information extracted from the short dependencies, but it's not different from using automatically analyze the sentences as training data. The training data is that were used is the same as the original training data. So the only feature sets were added to the original one.
So I have one question. So you are developing like dependency and phrase structure annotated corpus in both Japanese and Chinese. So are you planning to use like syntactic transfer system for your machine translation?
Yes. Yes, it's important to use the target or both language structures to improve the syntactic structure analysis performance. So we think we are planning to apply the method proposed by Professor Matsumoto. They used the structure of the target language to improve the accuracy of the source language dependency analysis. Yeah. But that will be the baseline. So we have to we need some good idea to utilize the information in the other language. Yeah.
You said you had about a million sentences,
Yeah.
sentence pairs
Yes.
in the scientific domain.
Yes.
Will have.
Will have, yeah. And now,
Given that the scientific domain has significant lexical gaps between the subdomains, the different subfields, is that going to be enough to train systems for each of those subfields?
we invest.
What were the subfields originally again? The fields, the scientific fields that you had. One was environmental science. One was
Three main target fields, but there are several other, maybe 50 fields we have to handle. And we selected several sentences from the other target domains, and we investigated the coverage, and almost 1/3 of the whole corpus covers the almost 9% of the whole corpus. We found we extracted 1/3 of the whole corpus, and that covers over 90% of the whole world statistics.
Okay, so that's lexical coverage.
Yeah, it's lexical. Yeah. And I don't think it's enough for a machine translation, but so we are planning to develop the techniques for domain adaptation. But at least we need several a small corpus for each domain.
Evaluation.
Anyway, okay, thank you very much.
Thank you.